Objective 2.4, Factoring and Solving Polynomials, Part 1. So in today's lesson, we want to be able to factor polynomials using various different methods. And so what I have listed here are the different methods we'll be using. We'll be looking at factoring with greatest common factor monomials. We'll be factoring polynomials by grouping, factoring polynomials in quadratic form. Hang on just a second, let me get rid of this for us so we can keep going here. Okay, so polynomials that are in a quadratic form, factor the sum or difference of cubes. That might be something a little bit new. And then in all of that, being able to use our factoring methods as ways of solving polynomial equations. So a little bit of vocabulary to get us started that's going to help us with each of these methods. First, you see the two patterns that we can use for the sum of two cubes or the difference of two cubes. And take a close look at what this pattern really is. This pattern is showing that if I have addition here, then in my first binomial, I'm also going to use addition. So these two are going to match. Okay? And the A and the B in this binomial come from this base. So whatever it is that's being cubed to give us the first term, whatever it is that's being cubed to give us the second term, that's what the A and the B are going to be. Okay, and then we multiply that by a trinomial, and in the trinomial our last term is always a plus, but this term will always be the opposite of what that one was. So in this case, with the sum of two cubes, addition here tells us addition here, and then subtraction is going to be here. But notice in the difference of two cubes, since we're starting with subtraction, we have subtraction here and then addition and addition. So again, this is the opposite of this one, but this one stays the same. Okay? The next vocabulary phrase is the factor by grouping, and there they're just explaining that we're going to group pairs of terms together that have a common monomial factor, and then we're going to factor that common factor out and look for a pattern. So we'll see how that works in just a minute. And then we also have factoring polynomials that are in quadratic form, and a quadratic form looks something like this, where we have a first term that has a coefficient a times something squared. We have a second term that has a coefficient b times whatever that something was that was getting squared in the first term. And then we have the addition of a constant c. And notice here it says u can be any expression in terms of x. Okay? So when we're doing these kinds of factoring polynomial problems, we can fall back on what we know about quadratics already to help us solve this. It's going to be a little bit different because they're not quadratics, they're higher degrees than that, but because of the way they're set up, they're in what's called the quadratic form, and so we can use that form to help us. So we're going to be using a lot of methods today that are based on things that we've already talked about, based on ideas that are going to flow very naturally from previous lessons. But the reason we're calling this part 1 is because there are times where these particular methods don't work. So part 2 in a couple of days is going to be looking at what do we do when the methods from today don't work. So these are very specific methods. They work in very specific situations, and when they work, they're great methods to use. But they don't always work. So when they don't work, we'll be looking at some methods in part 2 of how to deal with that. All right, so here's our first example, and in this example we want to factor by finding a greatest common monomial factor. So when you look at the equation x cubed plus 2x squared minus 15x equals 0, you want to look at each term and determine if there is a common monomial factor. So in each of these three terms, we can see that we have a common factor of x. And remember that when we factor this x out, okay, when we factor this x out, we are dividing it out, right? And so this remaining trinomial is what we get when we take each of these terms and we divide it by this monomial. Another way of saying that is if I redistribute this and multiply it back through, I should be able to get back to what I started with. Okay? So when I divide out an x, I end up with x squared plus 2x minus 15 as the trinomial that's still in the parentheses. But that trinomial now is also quadratic. So now we can use our quadratic factoring methods to see if we can factor even more. And we can. The factors of negative 15 that add up to a positive 2 are a positive 5 and a negative 3. So we now have the factors of x, x plus 5, and x minus 3 that end up being equal to 0. Now, here's where our zero product property comes back into play. Since we now have three factors, and the product ends up being equal to 0, then that means any one of the factors could have been the 0. And so our solution is based on what are the values of x that will make each of these three factors equal 0. And so we end up with a 0 as one possibility because the factor of x set equal to 0 is just 0. From x plus 5, if we set that equal to 0, we get x equal to negative 5. And from x minus 3, if we set that equal to 0, we get x of positive 3. So three possible solutions here for this equation are x equals 0, x equals negative 5, and x equals 3. Now how about the next example? We have 2x to the 5th minus 18y cubed equal to 0. So again, we want to look for a greatest common monomial factor. What are the factors that each of these two terms have in common? And in this case, that's 2 and y cubed. So if we divide out the 2 and the y cubed from each term, we're left with y squared minus 9. Now again, if we look closer, we can see that the y squared minus 9 fits a quadratic pattern of difference of squares, and so we can factor that even more and come up with 2y cubed times y plus 3 times y minus 3 equal to 0. So again, we are left with three factors with a product equal to 0, and so zero product property says set each factor equal to 0 to find out what the possible values of your variable could be. So my 2y cubed equal to 0 is going to be 0. My y plus 3, if that's equal to 0, that will equal negative 3. And my y minus 3, if I set that equal to 0, I will get positive 3. So my possible solutions for this equation are y equals 0, negative 3, and positive 3. All right, now it's your turn. Take a moment to work out this guided practice problem. Don't forget to answer the Zaption question that will be to the right of your screen. Use the same methodology that we were just showing you in the example problems on the previous screen. And when you think you have your answer figured out and you've answered your Zaption question, then come back and check your answer. All right, so our greatest common monomial factor in all three terms is the 4z squared. So when we divide that out, we end up with the trinomial of z squared minus 4z plus 4 in the parentheses. That can be factored another step into z minus 2 times z minus 2, or z minus 2 squared. And so we now have these two factors whose product is equal to 0. And so if we set each factor equal to 0, we get z as a 0 and we get z as a 2. Those are the two possible real number solutions to this equation. All right, moving on to our next method. This is called grouping. And grouping is something we've already seen a little bit in the quadratics, because this was the method I showed you how to use when you did the split the middle method. Okay, so this might look familiar to you. I hope it does. Grouping works best when you are dealing with a polynomial that has 4 terms, because that allows you to group the terms into one pair of 2 and another pair of 2. So a trinomial is not going to be a good situation for this. 5 terms is not a good choice. This works best when you have 4 terms. Okay? And so the method here is to actually group the first 2 terms together and the second 2 terms together. Now notice in this case, I had a negative in front of the 4x here. But when I put my parentheses around this group here, and then this group here, I want this negative to stay part of that term. And so you notice what I did here is I kept the negative with the 4x, but I changed it to addition in between the 2 parentheses. Okay, so I changed this subtraction into adding the opposite. And then that negative stayed in the parentheses with my 4x. Okay, that makes this process a bit easier if you remember to do that. Try to always keep this sign in between the parentheses as a plus. All right, so you can see then that from there I looked at this first group and realized that x squared was the greatest common monomial factor. So x squared comes out and we get x plus 1 left as the binomial in the parentheses. Now here in my second group, I could just factor out a 4. But if I only factor out 4, I have a negative x minus 1 left. And the whole reason for doing factoring is to get this binomial to match up with this binomial. So this would not have done it. So instead I want to factor out a negative 4. So when I take negative 4x divided by negative 4, I get positive 1. And then when I take negative 4 divided by negative 4, I get plus 1. And then my 2 binomials match. And that's exactly what I want to have happen. I want those 2 parentheses to match. Because now, with them matching, now the x plus 1 becomes the common factor. So this is an entire term. And this is an entire term. And in those terms, we have the common factor of x plus 1. So just like taking the x squared out in front of this first group, I'm now going to take the x plus 1 as a common factor out of this whole thing. So if I take x plus 1 out of here, then it's the x squared that's left, and that goes right there. And if I take the x minus 1 out of here, then it's this negative 4 that's left, and that goes right here. And so now I have two factors being equal to 0, which are x plus 1 and x squared minus 4. Now at this point, you want to take one more second and check your factors and see if anything can be factored any more than what it already is. Because in this case, it can be. Our x plus 1 is about as simple as we can get, but our x squared minus 4 is again a difference of squares. And so that can be factored another step into x plus 2 times x minus 2. So now I have three factors being equal to 0, and I need to set each of those factors equal to 0 to find my possible solutions. So x plus 1 equal to 0 gives me negative 1, x plus 2 set equal to 0 gives me negative 2, and x minus 2 set equal to 0 gives me 2. So my three possible 2 and positive 2. All right, your turn to try grouping as a method. Pause your video for a moment, do the work, answer your Zaption question, and then come back when you're ready to check. If you're not sure you're ready to do this, rewind the video, go back, rewatch that example 2, and then give this a try. All right, so similar to our example in the previous screen, we can see here that we have negative 16. And so we want to change that to plus the opposite and keep the negative with the 16 in our second group. And then we factored out the x squared here. We factored out the negative 16 here. And we ended up with the x minus 3's as matching parentheses. So that x minus 3 comes out here. And then we're left with x squared minus 16 there, which can be further factored into x plus 4 and x minus 4. So our three factors end up being x minus 3, x plus 4, and x minus 4. Since the product they give us is 0, then setting each factor equal to 0 gives us our possible solutions of 3, negative 4, and positive 4. All right, next method. In this case, we want to find the real number solutions by factoring something that looks like something we saw when we worked with quadratics. It's not quadratic. This is a fourth degree polynomial. But it looks like something we saw with quadratics because it looks like we have a difference of squares here. And indeed, we do. You can rewrite this as two terms that have each been squared to give us the 25x to the fourth and the minus 9. So the term that has been squared to get 25x to the fourth is 5x squared. Right? If we're taking 5x squared and squaring it, both the 5 and the x squared get squared. So that gives us 25x to the fourth. For the 9, obviously, we're just squaring the 3. And so when we go to split this up into the factors, it's the 5x squared that we use for our first term, and our 3 that we use for our second term. And so we end up with 5x squared minus 3 and then 5x squared plus 3 as our two actual factors. Now, when we go to set each factor equal to 0, when I set 5x squared minus 3 equal to 0, I'm going to get x squared equal to 3/5 because I had to add the 3 and then divide by 5. But because that's what x squared is equal to, not just x, I have to work a little bit more in order to get x by itself. So that means I'm going to have to take the square root of my 3/5, and don't forget that that's got to be a plus or minus square root because we are in the process of solving an equation. Okay? Now what that means is this is the same as the square root of 3 over the square root of 5. And we know from our previous chapter that we cannot leave the square root of 5 in the denominator. So we need to rationalize by multiplying by the square root of 5 on the top and the bottom. So square root of 5 times square root of 5 is where our 5 comes from without a radical. And then in our numerators, we're taking the square root of 3 times the square root of 5, which is how we get square root of 15. And you notice we still have that plus or minus out in front to give us two possible x values. So, from our first factor of 5x squared minus 3, we end up with possible solutions of positive square root of 15 over 5 and negative square root of 15 over 5. And again, notice we cannot simplify this anymore. I cannot take the 15 divided by 5 because the 15 is inside of a radical sign and the 5 is not. So this is as far as I can go for this answer. Now with my second factor, my 5x squared plus 3, if I get my x isolated there, I end up with a step where x squared is equal to negative 3/5, because in this factor I had to subtract the 3 first and then divide by 5. So if I were to continue this and take the square root of both sides, I would end up taking the square root of a negative. Now, you may be familiar with complex numbers and what would happen with that from our last chapter, but they're not asking us to come up with complex answers. They're only asking us to find real number solutions. So even though you know how to deal with this, they're not asking you to deal with that. They're only asking you for real number solutions. So, based on the directions, our only answers are going to be the plus or minus square root of 15 over 5. Now, if they'd asked us for all solutions, then we would continue working with that negative 3/5, take the square root, use I to get complex answers, and all of that. But it's not what they're asking us for, so that's not what we want to give for an answer. All right, here's another one that fits a quadratic form. Again, it is not a quadratic, it is a fourth degree polynomial, but it kind of looks like a quadratic. And so that's the last statement that they gave you in the vocabulary box. This is what we can consider when dealing with this. We can say, well, if I can somehow rewrite x to the fourth as something being squared, and then if that ends up being times negative 6, or excuse me, that ends up being combined with negative 6 times that same something, and then plus 9 equal to 0, then I can use the quadratic form and I can actually use what I already know about quadratics to solve this and to factor this. Okay? So we can rewrite x to the fourth as something squared. It would be x squared squared. We also notice that that's the same thing that's being multiplied to negative 6. It's an x squared. And so what we do is called u substitution. We're actually going to substitute u in place of x squared for just a moment so we can actually work with this equation as if it were quadratic. So this is a very legitimate method. It actually has a name to it called u substitution, and it's kind of like if you think about sports, okay? Let's say x squared is the starting player on the basketball team. So x squared starts the game. But then coach wants to run a particular play, and so he calls you off the bench, and he tells you what the play is, and then he substitutes you in for x squared, and x squared comes out for a moment. So we are literally going to put u in place of x squared in those two parentheses. So now we're just dealing with the quadratic of u squared minus 6u plus 9 equal to 0. And now we're just going to act like this is a quadratic equation, and we're going to use quadratic methods to factor it. And when we do that, we end up with u minus 3 times u minus 3, which is u minus 3 squared, equal to 0. Okay? So from that, we come up with u being equal to 3. But our original equation was not in u, it was in x. And so in order to get a final answer, we need our solution to be about x. So now that u has run its play, we'll call it the quadratic play. So it's come in, it's run its play, x squared has gotten a chance to rest for a minute, and now coach sends x squared back into the game, and u comes out. So x squared is going right back in for u, and now we're dealing with an equation of not u being equal to 3, but x squared being equal to 3. And so now we do whatever we need to get x by itself from there, which means in this case, square root both sides, and we end up with x being equal to plus or minus the square root of 3. Okay, so that takes us all the way to the end of what our final answer should be, what our x solutions should be. But to get there, it helps if we do a u substitution. Because by substituting u in place of this x squared, we can now just think of it as a quadratic. What would we do with it as a quadratic? Solve it out that way, and then substitute x squared back into the game to finish it out. Okay? All right, so why don't you try one? See if you can use this same method of using u substitution and solving the equation as if it were a quadratic. Answer your question on the side, and then come back when you're ready to check. All right, and so if we do the u substitution and we put u in for x squared to run the quadratic play, then we end up with a u minus 8 quantity squared equal to 0, and so u would be equal to 8. But then when we sub x squared back in, then we finish that out by taking the square root of both sides, so that gives us x equal to plus or minus square root of 8. But again, we want our answers to be simplified, and so we would simplify that to plus or minus 2 square root of 2. Even though those are square roots and they are irrational numbers, they are still part of the real number box. And so this is a perfectly legitimate answer to come up with for real number solutions. All right, our next example is specifically about cubes. So this method only works when we're talking about adding two cubes together or subtracting two cubes from each other. But the pattern always works, which is kind of the cool thing. So this is the pattern that was one of the first things that they gave you in that vocabulary box. You want to refer back to that in your notes. We need to start by figuring out what is the a and the b. So what is the thing that's being cubed to give us our first term of 64x cubed, and what is the thing that's being cubed to give us our second term of 1? So that ends up being a 4x for the first term and 1 for the second term. So our a is 4x and our b is the 1. So using that and using the pattern, we can set up that our binomial factor will be the 4x plus the 1, because remember we're going to keep the first sign the same. And then in our trinomial factor here, we're going to take the first term squared minus, because that's the opposite one, the first times the second term, and then always plus right here the second term squared, which is just 1. So now if we do some simplifying here, we can square our 4x to get 16x squared. We can multiply our 4x times 1 to get our minus 4x, and then again that 1 squared just gives us 1. So we have a linear binomial factor there at the beginning, which will be easy for us to find a solution for. But then we also have this quadratic trinomial factor. And so we need to see if there's any way that we can solve that quadratic. Now it doesn't look like factoring is going to be a particularly easy process with this, given that we have 16 for an A and 1 for a C, and we're trying to get a -4 for B. So if factoring doesn't look like it's going to work here, let's just test out quadratic formula for a second. So if I use the quadratic formula on that quadratic factor, it would look something like this. And I would end up getting a square root of -48, which means I would not be able to get real solutions from that quadratic. So the only solution I actually get to this equation is the solution I get from that first linear binomial factor, the 4x plus 1. And when I set that equal to 0, I'm going to get x equals -4. So that is my one and only solution to the equation 64x cubed plus 1 equals 0. Okay? That is pretty much always going to happen, that the quadratic factor that you get from using the sum or difference of cubes pattern is going to be a quadratic that does not give you real solutions. So if you are specifically being asked for real number solutions and you've done your factoring into your binomial times your trinomial, you only need to use that binomial linear factor to get your actual solution, because the trinomial quadratic is not going to give you real number solutions. Okay? Let's take a look at another one. This time we have a difference going on, and it looks like we have a cube in the first term, but 24 really is not a cube. And so what are we really supposed to do here? How are we supposed to use the pattern in this case if 24 is not something being cubed? Well, one of the things you always want to consider when you talk about factoring is that you always want to look for that greatest common monomial factor first. Because in this case, 3x cubed and 24 both have a common factor of 3. And if I factor that out first, or even divide it out to get rid of it, then I end up with an equation of x cubed minus 8 equals 0. And now I have a difference of cubes. The x cubed comes from a base of x being cubed. The 8 comes from a base of 2 being cubed. And so x is going to be my A, and 2 is going to be my B, and my pattern is going to work. So my first binomial factor is just simply going to be x minus 2. Again, remember, signs are going to match, so minus is going to give me minus in the first factor. And then in my trinomial factor, I'll take the x squared plus, there's that opposite sign, plus the x times the 2 plus the 2 squared. So with a little bit of simplifying, I end up with x minus 2 times x squared plus 2x plus 4 equals 0. And again, just to show you that we only really need to worry about that first binomial linear factor. If I use the quadratic formula on the x squared plus 2x plus 4, you can see again, I end up with a negative inside the radical. Okay, so just showing you once again, the quadratic is not going to give me real number solutions. So I'm only going to look at that x minus 2 factor, and it's going to give me a solution of x equal to 2. All right, why don't you try one now? Use the pattern for the sum or difference of cubes and answer the Zaption question when you think you've got an answer, and then come back and check it to see how you did. All right, so in this case, our A is going to be x, because x cubed is what gives us our first term, and our B is going to be 5, because 5 cubed is what gives us the 125. So our binomial factor is x plus 5, and our trinomial factor will be x squared minus 5x plus 25, and then just looking at the x plus 5, setting that equal to 0, gives us a solution of x equals negative 5. Now you may be looking at this right now and thinking, well, you know, why am I going through all this? I could just say, well, x cubed would equal a negative 125. And so if I just take the cubed root of both sides, then I get x equals negative 5. Same answer, which is good, because it's the same equation, but a little different method. And you're right, that does work. It does give you the same answer. But the purpose of this particular lesson is to practice factoring. And so we want you to be practicing the factoring of these sum and difference of cubes in this lesson, because it will be a skill that you need in upcoming lessons. So it's not that this is the only way to do it, it's just that we want you practicing this skill in this lesson. All right, so you've got 4 different methods that you should be using as you work through your practice problems for Objective 2.4 in your booklet. If any of this wasn't completely clear, find the resources you need to answer your questions. Go back and look at the video, ask Mr. Frereking for some help, look in your textbook, but don't let these just go if you don't quite understand, because this kind of factoring is something that we will not only be using in this chapter, but we will be using it in future chapters as well. So you really need to practice and make sure you understand all of these factoring methods in this lesson now, so that when we see it again in the future, it will not be a difficulty for you. Make sure you check your completed practice with the answers posted in Canvas. And if you have any real immediate question, you're always welcome to email me. If there's anything that's not working well, again, just remember to email me as we continue to keep kind of tweaking how this is going to work and keep making this the best experience possible for you guys to learn Algebra 2. Okay, so that's it for this lesson. We'll see you next time.